Okay, what we're going to do today is we're actually going to start solving problems. Relatively simple problems, but what we're going to be doing is solving for some unknown things. And generally there'll be cables or bars or something like that. So we're going to be looking at particle equilibrium in the two-dimensional sense, so in the planar sense. So think of it in terms of the chalkboard or something like that. It's going to be there. We're not going to be looking, we'll be on Thursday looking at the third dimension there. So we're going to be looking at things in terms of x and y. Now, just to kind of go over what you should have read, and we'll put it in the context now of the vector algebra that we're going to be using as our tool in terms of solving for this thing. So Newton's first law, basically things at rest are at rest and that sort of thing. What we're going to do is pose it now in terms of our vector algebra. So what we're saying then is that the resultant of all the forces, and what we'll find is sometimes that's the problem, especially when we get into rigid bodies, we sometimes forget the forces, and we'll find that we'll get the wrong answers in that particular case. But resultant of all the forces, according to Newton's law, should be equal to 0. And this is, of course, so a body at rest, basically the couch potato, all the forces that when you're sitting there at the table, all the forces acting on you are going to equal to 0. Or moving at a constant velocity. Best way to visualize that is if you're on a light rail train or a bus or something like that. When it starts up, there's accelerations, you feel movement, you're having to catch yourself. But once it's moving along there, you can stand like you were standing whether the bus was still or moving at that constant velocity. So those are going to be the two places where we're going to be able to apply statics. In terms of our vectors, okay, we'll have a set of forces acting on a point. Now the point doesn't necessarily, we'll talk about that, doesn't necessarily have to be small, but basically they're all intersecting at that one point there. Remember when we were constructing the resultants, we were doing that tip to tail construction. You remember the 1/2 of the parallelogram, so we'd look at the top half or the second half. What that says then is if I start at a point with my F1 and then I add one of them, it doesn't matter which one, what that implies in terms of our vectors is that we end up to the same spot. So remember, we were pushing the book around and coming up with resultants. Resultant of all the forces, so this is all the forces acting on this point. If I do a tip-to-tail construction, what I should find is that all of the forces end up in the one spot. We start at one point. By the time I get done, equilibrium says, then I need to end up in that same spot. And it doesn't have to be 3 forces. It could be 4, 5, 6, and that sort of thing. And what that means then is that the final resultant vector, when you think about it, if we end up at the same point, if I try to add them all together, I'm going to get nothing. I should get nothing, no direction, no value in terms of magnitude. Now the other thing we did was, remember, we broke things into x and y components. We kind of like that x and y situation there where they're perpendicular to each other, although we can set up, and one of your homework problems was actually looking at a problem where they weren't necessarily perpendicular. Remember then, our another way we constructed that was taking all of those forces, and what we're saying then is that if we add them up via components, we should expect to see a 0 at the end there. Now let's think a little bit about that. When is a vector equal to 0? Another way we can express a vector, remember, is in terms of those magnitudes and those unit vectors. So there's a magnitude of r in the x direction and a magnitude of r in the y direction there. If I set that equal to 0, what does that mean? How does a vector go to 0? And some of you that had my class before, be quiet. Let's see if we can get some new people in here. Remember that from vector algebra? What makes a...
When all components equal to 0 vector.
When all components are equal to 0. So that one and that one equal to 0. Okay? So when we think about those two components, what we really have is two equations like this. Because remember, the Rx components are just simply the x components of all the forces, 1, 2, and 3. And the y component of my resultant is just simply a summation of all the y components of those individual forces. Being careful, again, that we're applying minus signs and plus signs based upon a coordinate system we set up. Now the nice thing we have two scalar equations with a 0 at the end, which means then I can solve for one thing on the inside there. I've set my right hand equal to 0 now, so therefore in most two-dimensional senses, if the particular particle is in equilibrium, then I can solve for two unknowns. So again, let's just think about what we have in terms of a force here. When we express a force, we can express it in terms of its components. So when we think about what it looks like we've got a force like that. Now what that says is I can express that in terms of those two components. And again, what that's simply doing is forming a parallelogram, but it happens to be a rectangle, so a rectangle is a parallelogram. And if I have each of those components defined, what I've defined then is I can find the magnitude I can define the magnitude through Pythagoreans. That's the nice thing about having a perpendicular coordinate system like that. And I can express the angle then based upon some coordinate system, same coordinate system, obviously. And I call it theta x because I'm measuring it with respect to the x-coordinate. So what we see then is there's really two ways of expressing a force. Remember, a force is going to be a vector, which implies it's got a magnitude and a direction. I can express it directly as a magnitude and a direction based upon a coordinate system I set up, or I can express it in terms of x and y components. Now note, if I've got a fixed angle there, then the x and y components are got to be fixed, right? So if I solve for one and I happen to know the angle, I can solve for the other. Now the key thing though is each force has two unknowns to it, okay? It's a single force, but there's two things we need to define, either x and y components or a magnitude and an angle. So when I solve for a force and I have the ability now to solve for unknowns, I can solve then for a single force if I don't know its direction. So just to continue that. So if I have an unknown force in an unknown direction, I can solve for one force. I have to have two equations basically to solve for that. Oftentimes, if I know the directions, and we'll see a lot with particle physics, it's going to be cables and stuff. We'll know the direction of the cable. It's going up, down, over, sideways, and that sort of thing. We'll know the direction. If we know all of the directions of the forces, all the cables or bars or whatever that's attached to the thing there, then what we can solve for is magnitude. Yeah, I spelled that right. Okay. So I can solve for two. We think of it as forces, but I'm only solving for one piece of the force. So I'm completing it because we know the angle of those particular things, but I can solve for two magnitudes of forces in that particular case. Okay, so equilibrium 2D, there's going to be really two steps we need to think about. And you will need to do both of them, basically, to come up with anything. First step, there's no free lunches, but there are free body diagrams. So a free body diagram is a term you'll see, especially when we get into rigid. What we do with this, and I will use a shorthand as we get going along there so I don't have to write it all out as FBD. So that's a free body diagram, basically is going to be our tool to learn how to spell. So we're going to use that as a tool to identify the forces. We're going to use that if we maybe know the directions. We'll put that on our free body diagram so we know that we can start solving for magnitude. Or we might find that we have a force that we don't know exactly where it goes and which direction it's going, so we might be able to solve for 1. That's our first step. So we need to use that tool to figure out what forces we're going to be assembling. And again, remember, we talked about the resultant being all of the forces equal to 0. So one of the difficulties, it won't be so hard here in particle physics, but when we get into rigid bodies, to make sure that we identify all the forces. We need to think about all the forces that are there. And then finally, we're going to use these equilibrium equations, these scalar equations that we have. So we're going to be able to start solving for those and putting a 0 on the end there and setting that resultant equal to 0. And this is our tool. And this is our tool for solving the unknowns. Now, the unknowns might be magnitudes. The unknowns might be angles. We don't know yet. But it will allow us to solve for those unknown pieces. Okay, now I'd like to go through the free body diagram construction. Your author does it too, but I'd like to go through the steps. You don't necessarily have to do them in this order, but I just want you to have the steps so when you start thinking about a free body diagram, you know what you need to be put in there. So 1's pretty easy. And for our first step here, it's just going to be a particle. So it's going to be a real easy one. We're going to draw a dot, basically. So we need to figure out where that intersection of all those forces are. And it sometimes goes without saying, but including some of the unknowns. We use that basically to identify those unknown forces or magnitudes or directions, whatever it is. So we want to include those in one of our free body diagrams. Not too many. If we do more than 2, then we can't solve it, but we might be able to play around with it a little bit. Now this one doesn't make a whole lot of sense right now because we're drawing a dot, but when we get into rigid body diagrams, this will be something we need to consider. I'm just putting it so we can consistently carry that through into our rigid body. Okay, the important thing is basically putting all those forces acting on the body. And I break it up into the subset of so the two sets of forces, we obviously want some known forces on there too, because we need some pieces in our equations that we know. And then we're also going to be then putting in forces in the unknowns, or where they're going to come from is basically some sort of a support that we've looked at or some sort of a body that we've cut away. So again, what our free body diagram is an isolated mechanical system. It's going to be the system we're going to look at. We're going to look at it by itself. And where there's cables, bars, any sort of thing supporting it, we're going to take that away. And what we have to substitute in is the forces that those things do. When we think about it in terms of a cable. If we cut a cable away, well, if we look at that dot there, that particle, well, we know that cable is applying a force to it. So we're going to be putting those in as the unknown forces. That's our first 3 steps. We want to label things because when we start putting things into our equilibrium equations, we want to be able to identify that it's this force we're talking about or that force we're talking about. So things like coordinate axes. We get to pick those. They don't have to be horizontal and vertical. If we find it's more convenient to set it at 45, we might want to do that. But again, if we're going to be putting in those things in terms of the coordinate pieces of a force, we're going to need the F1x and the F2x. So we have to define our system there. And again, if you don't have it on your free body diagram and you throw it in an equation, I don't know how you got it there. So you need to identify your coordinate axis. Your necessary dimensions. Now, I say necessary because you're sometimes going to be, as an engineer, most of the books and homeworks, they'll give you the necessary dimensions. But when you get in the real engineering world, you're going to find out you have a whole lot of extra dimensions there. But the ones you need in terms of setting up angles and that sort of thing, we'll see that we go ahead and put those in. So we can see that when we put those in the equilibrium equations, I can go and say, oh, OK. I know where that angle is now because you identified it for me. And then points of interest. We might have 2 or 3 dots out there. Well, identify one as an A and one as a B and that sort of thing. So I know you're working on this one or working on that one and stuff like that. So just points that basically you need to identify that help you when you get into your equilibrium equations. So that's basically the crux of a free body diagram. A couple of them don't make a whole lot of sense right now, but you really need to put all of that in order to be able to set up your equilibrium equations to solve for those unknowns. And again, if you forget one of the forces, you might find that you can't solve for anything, or you solve for the wrong thing. Equilibrium. OK, so one way is using our component system there, where we break down every one of those forces into an x and a y piece, and then we sum them all up, paying attention to signs, whether they're positive and negative, and setting a 0 in the end there. Now, since we have 2 equations, sometimes we might have to solve them simultaneously. We may not have all the information in one versus the other, but basically we can go through it. In this particular case, it's pretty simple. The other thing if we have 3 forces, then just like I did that drawing there, remember we had the 3 forces there. If we have a triangle, we can use those law of sines and cosines. So we can draw that if we can determine those internal angles there. And what we find is sometimes that's a lot quicker. Now, when we get into multiple forces, 4, 5, 6, and stuff like that, it's difficult to use this because then we have to create resultants and apply the force triangle 3 or 4 times. It's far better, and then what your computers do, basically, when you look at finite element or structural programs and that sort of thing, they're basically just breaking it into those components. Okay, so one of the things we're going to find, one of our restrictions in terms of our particle equilibrium is that the forces must be concurrent. One of those way cool words we can impress our English major friends with. What that means is the lines of actions of the forces pass through one point. And an example is we'll put up the traditional engineering baked potato. It might be some body like that. If we have a set of forces and lines of actions, LOAs, are just simply an extension of those. So it's basically a definition of the direction it's going. We talked about that in terms of sense and stuff. Now the two intersect. If we have a third one, the third one has to intersect if we're going to be able to apply this. Now we have tools that we're going to learn when we get into rigid bodies in chapters 3 and 4 on how to deal with forces that aren't concurrent. But basically, we have a set of forces on a big object. It could be a big object, but in terms of particle equilibrium, if they all intersect at a point, then basically we'll be able to apply those equations, those equilibrium equations. What that simply results in we can treat it like this. So we might have a big massive body and that sort of thing, but if all the forces go to a single point, then what we're going to find is that we're going to be able to express it like that. Okay, so grab your handouts, and from here on out, before we dive into it, we'll go ahead and start working on problems. Any questions?
Professor, do you have any more of those handouts?
Are there any in the back? I'm going to make sure she's printing out enough. Let me see if I've got any up. That's a hand in.
I can just follow along. I'll just copy.
Okay, yeah. Send me a thing I can send you. Actually, I might be posting one or two of them anyway, because I'm not sure we're going to be able to get through them all. Sir?
So for the homework, I did for the last problem, I did like a tip to tail method for the three forces instead of doing like a triangle.
Yeah.
So in order to do a triangle, you said you can do it with all problems with like three forces. You can just because I didn't see how I could do that with that one, just for the direction of each force. But would you just turn it into a negative to manipulate it to make a triangle?
Now, which homework are we talking about?
The last problem where the block was on an inclined slope.
Okay, because the homework we did was just simply calculating resultants, right? Let's see if I have the right one here. Because you're not doing, oh, okay, yeah, there it is. Yeah, all we were doing there, it's tip-to-tail construction there, but we're creating a resultant there. Okay, so that's basically putting them all together and then creating this R, okay? Now what we're saying here, remember, in terms of equilibrium using the force triangle is that I've identified all these forces, and what equilibrium insists upon is that if I take that, and these probably won't work out, but F1 is like that, F2 is like that, so F3 really should be more like this. What it says is if I take all of those and do a tip-to-tail construction, if it is indeed equilibrium, I should end up at the same spot. In other words, my resultant's equilibrium. So that's where, just be a little careful. That's resultants. This is now equilibrium. Same thing, tip-to-tail construction. But what we're enforcing here is that I know these forces now because I've identified them in my free body diagram. When I assemble them, they better do this if it's in equilibrium. So what you were doing basically in the problem 2, or homework 2, was just simply taking a set of forces and creating a resultant force.
Okay.
Yeah, so it would be like taking that one, and saying, okay, see, the arrows are all going in that direction. This one's saying, if they go this way, I've got to end up in the same spot. Yeah. And the other cool thing is, and I'm glad you actually brought that up, is notice here, we see those two are going that way, so we end up with the resultant going that way. This also helps us identify the direction of the force. Remember, in terms of when we talked about force, there's the direction component. So that angle, I can identify on with a coordinate system, that sort of thing. But also there was that sense. Is it going this way or is it going that way? So the other thing that tip-to-tail construction helps you with is okay, if you've got all those angles, it helps you let you know which one has to be going, which directions they have to be going, because it has to end up at the same spot. So you can use that to help you identify the sense of a particular problem. Okay, so any other questions? What we'll do is the first one there. Sorry, we're going to try to get something to be able to do this, or project it up on the screen there, but for now, you've got it in front of you. Okay, what we're going to do is the very first thing we need to do is construct that free body diagram. And I'll just kind of so in terms of when we look at that, I can look at forces at B, I can look at forces at A, but the one I'm interested in is C. Okay, so I'm going to choose point C. So that's one of the things you have to do is sit back and think, okay, where's the best place to do this? Step 2. Okay, so it's a really hard thing, a particle. So that's my point. My third step, getting those forces on there, and where did my red one get off to? Now, generally, I jump in and draw my coordinate system early, although sometimes you don't have to. And again, I said it's not important the order you do them in, but just make sure that you've got all of those little pieces there. So I'm going to, at point C, now note, what I've done is I've cut away that cable. Now what I'm going to substitute with that cable is going to be a force, because that cable is applying a force there. Now the nice thing about a cable is I know its direction, basically, so I know that the force isn't going to have a force going perpendicular to that. Wouldn't make a whole lot of sense. Cable, when you pull on it, it's going to give me a force in the direction of the cable. And where's my green? My green's dying. Okay, so I've got an angle of 25 degrees with a horizontal based upon the measurement I saw there at B. Okay, my FAC now is 600 newtons, so we've been given that in terms of the problem. And I know that angle is 45 degrees. And then finally, my other force there is that force P, which has an unknown magnitude, but also an unknown angle of alpha. And then just simply walking through our steps there. The other dimensions in terms of particle is just simply going to be the angles. Okay, so this is our free body diagram. We've used that. We've cut away, note, 2 cables there, and we're substituting in the forces that those cables provide that particle. And then we finally got that force P, which is applying some sort of an unknown force there on the thing. So we have a situation now where we have an unknown magnitude and an unknown direction. Now the nice thing is how many forces do we have? It's not a complicated question. 3, thank you. It's 3. So what we would try in terms of equilibrium is probably want to use the force triangle. And the reason you like the force triangle, especially if you have an unknown angle, you can usually figure out the angle rather quickly. So what we want to do is tip-to-tail construction, as suggested before there. So we'll pick a point and start our construction. So we go ahead and put on our first force. And again, if you're doing, this is why we like graph paper, because then we can kind of get these angles figured out and that sort of thing, and lengths. And the nice thing is that we've already identified an interior angle there, right? Because it's 25 here, and I know that one's at 45. And then tip-to-tail construction and equilibrium tell me that P has to end up back here. Now, in terms of other angles there, that's my alpha. We'll call this one gamma for now, and we'll call this one beta if we need them. Now, a couple things to note here, too, because I see this confusion a lot of times, too. This is a free body diagram. This is a force triangle. OK, so this is identifying forces. This is basically our equilibrium equations being applied in terms of a force triangle. So in terms of doing problems, you need to do both. You need to do this one to identify those forces. Is there 3 forces? Or are there 4 forces? Have I cut away another cable that I didn't pay attention to? If I've got those, then I'll end up going with the component system here. When I go to equilibrium, I can use this, but this is a force triangle. So I see a lot of people trying to use this as the free body diagram. Doesn't work. And not that you guys aren't smart. A lot of you can do this sort of stuff in your head. The issue is again, as engineers, we need to explain this to folks. And other engineers will be looking at it. If you don't explain it and it's all in your head, they're not going to accept it. They're going to send it back to you and say, explain to me what you did there and stuff. Plus, you might want to go back and look at it years from now and try to figure out what it was you did and stuff. So it's good to document all of your work. As engineers, we should be doing that. OK, so the nice thing is, note that my unknown magnitude is here. My known angle is directly across from it. So what equation should I use first? Cosines. And that's what my equation will look like. I go ahead and plug in the appropriate numbers. Oops. And just simply plugging and chugging, using your calculator and that sort of thing, we get up with a really nice big number like that. But again, that's p squared. We want p. And again, I show twice here, lots of digits, because I might need it for another calculation. Interior calculation. But in terms of reporting, I'm not going to report that. 5 digits, that, who cares about the 0.2 hundredths and that sort of thing. We'll keep it down to 3 or 4 digits. And then to find the unknown angle, we'll set up the equation like so. And again, note that I'm using the extra digits here, again, in interior calculation. So I'm going to plug them in there. I've got my known angle and my now calculated magnitude across from it. I'm trying to find this unknown angle, beta. What we find is that beta is 46.0 degrees. And we'll note that, remember our parallel lines there. So if this is alpha, then this whole thing will be alpha. So the alpha is what I'm interested in. That's what I need to report. The boss doesn't care about that interior angle there. So noting that alpha is just simply going to be beta plus 25. Oops, where's my... And what I can find now is that unknown angle there. And the only trick to be aware of is the fact that, in our forced triangle, we're using the interior angles. We might need to express our answer in terms of some sort of exterior angle defined by that. So just pay attention to those little details. Okay, before we go to the next problem, there's one other piece of physics that your author introduces later, and I don't know why, but it's an important one, and it's Newton's third law. We talked a little bit about that in terms of the first day. And that's the old action-reaction, right? And I'm going to define this again in terms of our vector algebra. That when we have a set of forces, we have an action and reaction going on. The key thing is that the force that's pushing this way is equal to the force pushing the other direction. I'm standing on the ground here. I'm putting a certain amount of force on the floor. The floor is exerting the same amount. If one was bigger than the other, I'd be launched into space or falling through the floor. Opposite in direction, obviously. But what's really important, and what the vector algebra piece of this is that it's on the same line of action. In other words, if I define an angle that that line is acting on there, then they both have to be on that same line. And going back to our cue ball picture there, again, if I'm drawing a free body diagram, I'm going to take a look at one of these guys. If I look at one or the other, what I'm doing is pulling them away from each other, separating them, but I have to substitute in the force that that other body's providing it. So if I look at just that one there, I'm going to see from this body here, when I take it away, a force that's acting along that line of action and has some sort of magnitude. If I look at this one, equal, opposite, and collinear is going to be the cool term we're going to be able to use there, but along the same line of action there. And the nice thing is then that says to me then, I can solve for this one, or if I'm looking for that force, I can look at that free body diagram, or I can look at that free body diagram. Just being aware of the fact that we're going to have to swap signs on it. So that brings us to our next problem, the pulley problem. Now, a couple of notes. Your author, we actually solve for this later in the course, and I don't know why he introduces you to pulleys and early on, but most of your other authors will use the term frictionless pulley. So what that implies then, if I have a cable going over a pulley like so, if I think about what those forces are, what it's saying to me, or we'll prove this later, is that if I have a tension of 100 pounds there, that's going to be the same tension. Actually, we'll just show the magnitudes there. So if it goes over a frictionless pulley, basically it's saying that if I've got a 500 pounds acting that way, well, the cable has to be acting 500 pounds there. It doesn't change its tension along the pulley. When we get into friction, we'll look at then friction pulleys that basically will change that tension. But for now and until we get to Chapter 8, basically all pulleys will be frictionless. And usually when I do it on exam, I'll say frictionless pulley. So the tension's the same as it goes across there. And the other thing, too, is that the pulley is generally quite small with respect to the problem. We've got these long dimensions of the cables and that sort of thing. So basically, we can treat it as a particle. It's a little off, but in terms of our ballpark estimates and that sort of thing, that's what we'll be looking at. So those are the two things your author doesn't necessarily tell you, but when you get into the homework problems, just be aware that that's kind of the rule we'll be applying until we get into Chapter 8 and look at other sorts of pulleys, frictional pulleys and bollards and stuff like that. Okay, so we'll look at a couple of different things here. We'll look at our pulley A. And then we'll note that there is a force, and we've been told that as 750 newtons being pulled down on that. So that's that P that we apply to that. So that means then for the cable that wraps across there and comes off at this angle, that's also going to be 750 newtons. And the nice thing about that is we also know that angle is 55 degrees. Is that right? Now there's also another cable attached to it that we're going to cut away. What did I call it? TACB. And note that that cable actually goes over C, so we're going to call it TACB because it's a one continuous cable there and stuff like that. And it's also at that 55-degree angle there. Now when we think about Newton's third law, we're going to draw our next free body diagram. And think about what we've got there now. We've got some forces there. We've got a Q, an unknown force, but we know its direction. The nice thing about things like weight and that sort of thing is we kind of know the direction is going to be perpendicular to the surface of the Earth. The cable that goes across the top of this is attached to the center of this one, right? So the other thing, we've got to keep track of all of these things. But that's going to be that 750 newtons, right? Because in Newton's third law, it says if the cable's there, 750, I cut it and look at the other pulley there, same direction. And I know that force there. And then the other things that are missing is that TACB. I've cut that away, but that's the one that now wraps under that pulley at C, right? And then it ventures off over to B. But it's the same thing because, again, it's a frictionless pulley, so the force on that side will be translated to the same force on that side. But this is coming off now at a much different angle, like so. And then this one we're going to go ahead and we're going to solve via components. So I'm going to set up my XY system. It's horizontal and vertical as we've done before. Now a couple things to note about this. Oh, the other thing that's missing here I forgot to put in is realize that that pulley is attached to the ceiling there. So there's a set of forces that will be acting on that pulley there that I don't know. So when we look at this one, we notice this one, ooh, it's got a lot of unknowns. We've got 3 unknowns. I've only got 2 equations of equilibrium. So that one's not going to be a very good free body diagram. But we highlighted that one to understand the fact that, OK, I've identified one known force. I identified this force here, equal and opposite, and then noting with the pulley requirement there that it's got to be the same on the other side there. And note then, in terms of unknowns, what do I have? What's unknown in this problem?
Total combined force?
Well, the magnitude, TACB, right? But I know the direction, right? I know the direction over here, and I know the direction of it over here. So the only unknown one in that particular one is going to be the magnitude. Happens to be going opposite directions, but again, and then Q. I know its direction also, right? So this particular case, I have 2 unknown magnitudes. So this particular problem, what we're going to do is use our equilibrium equations, but we're going to use the component forms. you can solve it both ways. And actually, the other problem you could solve both ways too. And I suggest, again, if you're going through them, solve them both ways. It helps you understand whether you've got the right answer or not. And I'll use EE not to convert you into electrical engineers, but that's equilibrium equations, basically. That's our equilibrium step here. So our I-hat pieces are going to be basically the sum of forces in the x direction. Now, one interesting thing here at this particular point, too, is we need to think about signs, OK? So when I say I'm going to sum my forces, you note here that when I look at the TAC ACB, I've got one going this way and I got one going that way. So I need to set up what I call my positive convention. And I'll just happen to choose it generally we choose it in the same direction as the positive x direction. But again, this is something you have control of. You can change it whatever you want. So we're going to choose the positive convention as the same as the positive x convention. And then we're going to look at all of our pieces. So we'll look at our first piece, our TACB. And what I want now is the horizontal component of that, which will be now cosine of 55 degrees. Will it be positive or negative? Negative, yeah, it's going that way, right? I define my positive convention of all the forces going that way. So I need to pay attention to my signs here. The other one I have is at 750, also at that same angle. Positive or negative?
Just kidding.
I'll throw you. Opposite. Opposite sense. So it's going to be going in that direction there. And then I've got my other piece there, the TACB. But it's at 25 degrees, and it's positive. Yes, you get the points for that one. And the key thing is equilibrium then says that all of my forces have to be in the x direction have to be equal to 0. The key thing, though, is make sure you pay attention to those signs. Very easy. And this is where you dictate the signs. Especially when we get into moments and stuff like that, it's crazy. You'll think, oh, OK, we think over here. You're setting up your positive convention here now in this equation. Again, you can set it up the opposite direction. Basically, we'll just swap the signs. Nothing to it. Now, again, we talk about forces having a magnitude and direction. Well, we got TACB going in both directions there. So I'll just indicate it basically, and we'll see this when we get into trusses. We just call it tension. We know the cable's in tension. I don't know of too many cables that work well in compression. OK, so that's our first part of that question. The second part, we're going to need to figure out what the Q is. Now, a couple of cool things here, too, to note. Again, you can set up your own coordinate system. Oh, question. That's a cosine of 55 degrees. That's a cosine of 25 degrees. Yeah, good question. No, I want everybody to understand that, so good thinking. Bring up those questions. If you're confused, you might help other folks. So there's no bad questions here. OK, the other thing, too, is we're setting up the coordinate system. Note that by setting up my coordinate system as horizontal and vertical, when I set up that first equation, the only unknown in it was the TACB, right? Q didn't appear. That's one of the other unknowns I got to figure out. Had I chosen a coordinate system at 45 degrees or something like that, then I would have had TACB, part of Q in it, part of the other TCAB. And then I go into simultaneous equations, which you can do, and easy to do when you're doing a 2x2. And you get into 3x3 and stuff like that. But again, when you start thinking about things like your exams, some of you will be taking the FEEIT exam and stuff like that. You want to think about, is there a nice coordinate system I can set up where I can eliminate one of my unknowns and just solve for one unknown? So part 2 is going to be our J pieces. The sum of the forces in those y directions. So I'm going to break all of my forces into y. And then, since I'm setting up my equilibrium equation, I need to figure out what my positive convention for that equation will be. And again, I can choose it as negative, but it's easier generally to do it in terms of the same direction as the positive y. So basically, what we're going to be doing is swapping our sines and cosines. But noting, we've already solved for this, so I'm going to be plugging in but I'm going to plug in the extra digits while I'm there. So I've got that in a positive sense. My next piece will be the 750, which is also acting up, just like students. So it'll be acting up in the positive direction. Now notice my other TACB will be acting in a positive sense also. So where we swap signs here, they're all going to be the same sign. And the only thing acting negative then will be my Q piece. So I'm going to add my Q. It's all in that direction, so I don't have to worry about sines or cosines on it. And what I'll find then is my Q will be a positive 2220 newtons. And we know that one's going to be then acting in the vertical direction there. OK, when you get a chance, then we'll look at the last problem.
In this case, wouldn't Q be negative? Negative force?
Good point. Great. I'm glad you brought that up. OK. Question was why isn't Q negative? Any thoughts on that? Why is Q not negative? It's going down, right?
Magnitude?
We're solving for magnitude. Where I assigned it in the negative direction was there. And it brings up a really good point. It doesn't make a whole lot of sense with particle physics, but when we get into rigid bodies and stuff like that, what we'll find then is then if we've been given a direction for Q, right? If I put it in properly and I had it drawn down in a negative sense there, if it comes out positive, what that tells me is that the direction I assumed is correct. Remember that sense that we talked about? There's line of action, which basically is an angle defined on some sort of coordinate system. But there's also, is it going this way or is it going that way? You don't know. Sense. If my answer came out as negative, and I did this correctly, I showed the force as acting negative, and it came out as a negative, that implies then I chose the wrong direction, or the wrong sense, I'm sorry. So if it comes out as negative, it just simply corrects us and says, you got the right direction, but your force is going that way.
And when does it take off full points on our homework for that? I had a question last night where I put in 32 and it said, no, it's negative 32 for the magnitude of a force.
Oh. Don't get me started on McGraw-Hill. Sorry. I won't be that vicious, but be aware that it's important, though, when you're designing something, you're designing a bridge. If you've got the force going in the wrong direction, you design the thing for tension and it's in compression or vice versa, and it fails, then you get into real big trouble. So it is important. Why it's 4 out of 10?
Yeah.
I got to talk to them. I don't have any control on how many points can be assigned to those pieces and stuff, so I apologize, but we'll struggle through it. I've got it set up so you should be able to go in and keep trying it though until you get it and stuff like that. So I want you to understand the problems, work them out, and if it comes out negative, I think you can go back in and actually try it again. Some of you had.
I was able to. Yeah, you can.
You can? Okay. Yeah. So I think you can resubmit the way we've got it set up right now. So go ahead if you want to keep working on it and you got the time, do it. And it's like I say, it's 10 points there, Get those 10 points. You're going to have to deal with exams and other such things to worry about. Okay, any other questions? So really good question. Thanks for bringing that up. So it's important, and we'll see this again, that signs will correct us. So as long as we got the direction correct, the sense will be figured out by the equations. Okay, so the next one we'll try to get started on. What I'll do is I'll get started on it, and what I can do is post the solution on the handout section. So tonight, I'll let you out because I know some of you have got to rush off to important exams and other such things. But we'll talk a little bit about this one, and the important thing is going back to Newton's third law here. Actually, we'll start off with point B. Okay, point B is the thing we're interested in. We've been asked in this particular one, we've got two weights on there. One of them's known. The one at C is known as 20 pounds. The one at B is the one we don't know. Now, what the problem says is for this to be in equilibrium, it has to be in a certain configuration. So we've got all of our angles defined there. And there's a certain weight that's going to achieve that particular configuration. So if we look at point B, we've got this weight that we're trying to find out, but we know it's acting in that direction. Whoops. Is that going to be TBC? Sorry, my pens are starting to die here on it. But we know that direction. It's 45 degrees. TAB and I like introducing this early too because this is going to be the magical 3, 4, 5 triangle. You're going to see it a lot. Okay? What's the sine of a 3, 4, 5 triangle? The sine of this angle here of a 3, 4, 5 triangle? 3 over 5. Remember, it's ratios. And cosine is going to be 4 over 5. So when you see something that's 3 over 5, or if it's 15 and 12 and 16 or something like that, realize that you've got a 3, 4, 5 triangle. You've got your sines and cosines in terms of real nice fractions there, or 0.8 and 0.6 if you want to use decimals. So we've got those. When we look at this particular problem, or this particular point, we've got too many unknowns, right? There's 3 unknowns. I've only got 2 equations of equilibrium. So what we're going to do then is then draw a free body diagram of point C. And that's at 60 degrees. Now the key thing is that note that TBC, the cable between BC, are going to be the same thing. So again, there's our Newton's third law showing up. Oh, rats. And then our other force is acting vertically, but we know that one. So what we're going to see, and I'll let you guys out on time, is then when I look at this free body diagram, I can solve for TBC, and I'll show you two different ways of solving it, free the force triangle and then components. But note, I can solve for this one. Once I solve for that one, I can come down here. This is now known. I have two unknowns, and what I can do then is solve for the unknown w's, which is what I'm after. So I'll post those solutions in the handout section of SAC CT.